Good afternoon. On behalf of my teammates and I will be introducing our lesson on fire safety in the fire tetrahedron. We'll begin by giving background information on the fire tetrahedron. On screen, you can see the simple model that represents the three necessary ingredients for a fire to ignite. The ingredients necessary for a combustion reaction are heat, fuel, and an oxidizing agent. All combustion events are chemical reactions between a fuel and oxidant source. These reactions require a certain amount of energy to initiate, which can be gained from a heat source. The triangle becomes a tetrahedron by the addition of the chemical chain reaction. The initial combustion reaction adds more heat to the system since these reactions are exothermic, resulting in the sustainment of additional reactions. This means that the fire will only go out if either the fuel, oxidizing agent, or heat source is removed from the system. Next, we will introduce the concept of critical combustion temperatures. The flash point is the temperature at which the fuel is vaporized enough to ignite. Meanwhile, the fire point is the lowest temperature fuel vapors will burn at for at least 5 seconds after ignition. Finally, the auto-ignition temperature is the lowest temperature which will ignite the fuel at atmospheric conditions without an ignition source. The video included on this slide was provided to you as a supplemental resource to learn more about these terms outside of this lesson. Finally, we will introduce the fire classifications. These classifications are used to categorize fires based off of the type of fuel involved in the combustion reaction. They are necessary because each fuel type combusts in unique ways and requires a unique method to be extinguished. The rest of the presentation will go into further detail about how fuel types impact the combustion reaction and the method to use to safely put out the resultant fire.
So let's break down the categories of fuels by starting with class alpha fires, which are common household items such as wood, drywall, paper, cloth, and other products. Wood, paper, and certain types of cloth are usually made of vegetable tissue. These are usually composed of hydrocarbons. Cellulose, which is essentially fiber, like celery. Hemicellulose, which has a weaker structure, but hemicellulose is strengthened by lignin, the final component of wood. And different types of lignin are responsible for the differences between harder, denser wood and lighter, softer wood. The lighter the wood, the more intensely it burns with a long flame. Because air is able to penetrate lighter wood easily, combustion will happen more effectively. However, in hardwood, since the structure is different, the penetration of air is more difficult and results in a concentrated flame that's hotter at the point of burning. Next, we have combustible metals like magnesium, titanium, and so on. The reactivity of a metal will increase with a finer particle size. Metal powders, for example, are very flammable. Each metal's ignitability will be different than the other, although once a metal is ignited, they will all burn very intensely and generate lots of heat. Though some metals are difficult to ignite, sometimes the heat of friction alone can be enough to ignite a metal. Moving on, we have flammable liquids and solids. Class Bravo fires are fueled by gasoline, diesel, propane, and other liquid chemicals. Class Kilo fires, on the other hand, are fueled by cooking oils. Though both Class Bravo and Class Kilo fires can be in liquid or gas form, the fire classes used in the US don't distinguish between gases and liquids. So Bravo and Kilo classes show up in both forms. Why is that? Well, it's to do with how each fuel type's fire can be quenched, due to chemistry and what situations they're found in. But we'll get to that later. Anyways, in order to burn, these fuels need to first get into gas form. Pools of fuel, such as a bucket of kerosene, are difficult to ignite because they are not easy to vaporize. Fuel and air do not mix well in this state, as every fuel needs a certain portion of air to react with. On the other hand, if a fuel is sprayed, the fuel can vaporize much quicker because it's already broken into little tiny droplets, ready to mix and ignite. It's also easier to get the fuel hotter if it's in droplet form. Finally, the last category, which are gaseous fuels. Once more, Class Bravo and Kilo fires can both happen in the liquid or gas states, so they're both listed here. Gas fuels are where we really get into the properties of flames and what makes one particular flame more vicious than the other. Flames burn most effectively when the chemical reaction is balanced. This happens when a unit of fuel reacts with the exact amount of oxygen it needs to ignite. If there's too much fuel, that's called a rich flame, and it'll be yellowish and you might even smell leftover fuel. If there's too much air, that's called a lean flame, and it'll probably be blue and burning cooler. Both of these flames will still result in flames, but a perfect balanced reaction will make the hottest fire. Different fuels have different ratios of fuel and air that will burn, called the lower flammability limit and the upper flammability limit. Too much or too little air, and the flame won't burn. Similarly to this, different flame types will result from different mixing types. If we mix the fuel and air together and then ignite a mixture, like in the engine of a car, the flame will most likely burn evenly. However, if we ignite some fuel without nicely mixing some air in first, like in a campfire, we'll see a different flame, as the flame will need to pull in oxygen instead of having us mix it ahead of time. There's definitely going to be too much fuel in the flame at first, and it'll probably be dirty and smoky too. Excuse me. Let's change gears for just a moment and talk less about fuel and air ratios and more about the flames themselves. Take a look at the diagram on the right. Let's say the reaction is balanced and the flames have access to air and it's all happily mixed together. The x-axis down here is the speed of the fuel and air, while the y-axis over here is the height of the flame. This diagram can tell us about how flames might react to disturbances. A slow-moving flow is short and gentle, or what we would call laminar, whereas a fast-moving flow looks spiky and violent, or what we call turbulent. You can see laminar right here and turbulent over here. On a still day with a supply of fuel burning steadily, one is likely to see the short and gentle flame, but move some air and cause a ruckus, and suddenly there might be a burst of activity. Keep this in mind while we talk about different extinguishers and why you might see each flame react differently.
So next we're going to talk about different types of fire extinguishers, specifically starting with water fire extinguishers. These can come in the form of a pressurized stream or a mist. The extinguishing method works by removing the heat. They are most effective on type A fires, so your common household material fires, but they are dangerous on types B, which are the flammable liquids, C, which are electrical, D, which are combustible metals, and K, which are grease fires. In this video right here, we're going to see why using a water fire extinguisher is a poor choice for a grease fire.
What you don't want to do is add water to it.
Really?
Okay. Let me show you. Let's step back.
Okay.
We got little squirters here filled with water. What we're going to do is we're going to direct these water streams into, so you might want to hold it up high.
Okay.
We're going to splash into that tray of oil, which is on fire. Ready?
Right.
Here we go.
Just normal water in here. Whoa. Wow. That I did not expect. Oh my gosh. Wow.
Okay. So you get the idea here. That's a tiny little tray. Nobody cooks with these little, I don't know what these are made for, maybe cornbread or something like that. Nobody cooks with one of those. You're going to have a much larger tray.
Right.
And if you added water to something on a much larger tray, I mean, that was a significant ball of fire. You can imagine in your home, what happens is you throw that water in.
So he continues to talk about what happens when you put water into a grease fire and how it evaporates and it takes the flame with it, and you end up with a much larger fire than you started with, which is why it's so important to never put water on a grease fire when you're cooking. Next, we're going to see using carbon dioxide as a fire extinguisher. So in this, we've got a normal candle, so like a small Class B fire. We added a little bit of paper just to make that flame bigger to see for this experiment. And so what is happening off screen is baking soda and vinegar are being mixed together right now. That reaction creates carbon dioxide, and that carbon dioxide gas is going to be poured from a pitcher on top of the fire. And so we will see what happens here in just a moment. I have to get a nice big fire just to help elaborate on what's going on. So here we can see it's about to be poured on, and you can see the fire is quenched almost immediately. So what is happening is that carbon dioxide is starving that fire of its oxygen, and that is how carbon dioxide fire extinguishers work. So they work by displacing the oxygen. They are most effective on type C fires. Type C fires are your electrical equipment fires. That is because they are non-corrosive. So if you have a electrical room on fire and you use a carbon dioxide, you can save whatever was not yet on fire of the electricals, whereas water might corrode it. They unfortunately are not very effective on type D fires, which are your combustible metals, as we'll see in this video.
We're going to use magnesium instead of aluminium. It's a little easier to set light to. This is magnesium turnings. I'm going to spread it out a little bit. All right. Okay, let's see if we can put it out. It will not go out with a carbon dioxide fire extinguisher. If anything, it makes it worse.
So he talks about how it will not go out, and that is because magnesium combusts about 3,300 Kelvin, which is about 1,000 Kelvin hotter than when carbon dioxide dissociates. Carbon dioxide dissociates about 2,400 Kelvin. So using a carbon dioxide fire extinguisher at this point, unfortunately, is making the fire worse because it has dissociated into its carbon and oxygen. Then oxygen is actually feeding that fire. So while carbon dioxide extinguishers are very useful, particularly in like industrial spaces and engine rooms, they unfortunately are not a solution for all of our different fire suppression needs.
So in this experiment, we're going to be showing how to put out a Class B fire or oil fire with a fixed foam extinguisher, and this is just going to be a make-at-home fire extinguisher. So what we have here is just a gasoline and oil mixture that lights really easily, and just a small amount of liquid so we can show the process. Oil fires are interesting because you can't just spray water on them. The water could splash the oil onto other surfaces and spread the fire. So the first thing we're going to show is this is a Windex bottle, but it's just filled with water. We're going to show how spraying this water onto the fire is only actually going to make it worse, so you'll see the flame grow. And then after that, we're going to switch to our makeshift foam extinguisher, and that's just going to be water mixed with dish detergent soap in a Windex bottle, so it'll give us a fine spray onto the fire. So this first clip we're looking at is the effect of water mist on a Class Bravo fire. So recall that in a Bravo class fire, it's not actually the liquid that's burning. As the liquid is heated up, those flammable gases are released, and the gases are what are actually combusting. So as the water is sprayed onto the fire, turbulence is induced in the surrounding air, and the flammable gases are dispersed. Thus, the flame grows substantially larger. And now the moment you've all been anxiously waiting for, testing the foam fire extinguisher. As you can see, the soap and water mixture is initially sprayed, a ball of fire grows with the turbulence that's induced. This is different from the water mist, however, in that a soap film is deposited on the fuel surface, creating a vapor boundary, which prevents further evaporation of flammable gases. Therefore, it physically separates the fuel and oxygen sides of the fire tetrahedron and prohibits further ignition. Foam extinguishing methods can be somewhat dangerous due to the probability, or the possibility I should say, of reflash. So in this clip you can see that after the foam was sprayed once, there wasn't a complete vapor boundary created such that flammable gases could still escape, and that was enough to reignite the fire, induce more turbulence, and spread to its original size. That's one of the issues with fixed foam, and one of the reasons why in industrial applications they'll actually flood an entire room with foam. It'll be a really thick layer to prevent that from happening. In summary, foam fire extinguishers can be used to create an oxygen barrier, which means they can be used most effectively on Class Bravo and Kilo fires. They can also be used for Alpha fires, but really the only thing that's doing there is providing cooling effect from the water that's within the foam. You can't really create that same oxygen barrier if you don't have a liquid fuel that's trying to evaporate. Similar to CO2, foam can be dangerous for Class Delta fires, and the reason for that is Class Delta fires burn so hot that the molecules dissociate, so the water that's in the foam actually breaks down and provides additional oxygen to the fire. Next, we're going to talk about dry chemical fire extinguishers. I'm just going to cover it briefly because there's a lot of different types and the chemistry can actually get pretty complex. But the way a dry chemical extinguisher works is it inhibits the chemical reaction and creates an oxygen barrier. So it's kind of like a 1-2 punch. It can be used on most any types of fire, Alpha, Bravo, and Charlie. This is typically what's going to be your standard household fire extinguisher, just because it's so versatile and it's quite effective. It also lasts for a long time. You don't have to recharge the extinguisher or anything like that. And once again, it can be dangerous on Class Delta fires, but luckily that's not typically a household fire we'd have. In conclusion, we'd like to tie this back to a real-life application of forest fires, which we also are so dangerous this last year. Depending on the types of materials that are being burned, the attack methods for putting out a forest fire can differ. There's 2 main classifications for ways to fight a forest fire, and that's direct attack and indirect attack. Direct attack is what you typically think of. It's anything that directly impacts the site of combustion itself. So wetting it, smothering it, putting chemical extinguishing agents on it, things of that nature. Whereas an indirect attack is something outside of that location. So the easiest example is a fire line some distance away that the fire is going to burn to, and then it runs out of fuel because that area has already been burned. Part of what makes forest fires so dangerous is the turbulence and convection in the atmosphere, particularly when you get temperatures burning it so high it only fuels the fire, and you can get things like fire tornadoes, and they can be really difficult to stop. So depending on what material is burning, They're usually going to use a combination of all of these methods to be able to put it out. At this time, we'd be happy to answer any of your questions.